Lecture 2, Metal Oxide Semiconductor Device, Physics. Having a solid understanding of semiconductor devices is crucial in analog IC design. It is not sufficient to treat each device as a black box, with its behavior described solely in terms of terminal voltages and currents. Attention must be paid to the internal operation of the devices. Moreover, as process nodes become more advanced, second-order effects become increasingly significant. Designers often need to make decisions about which effects can be ignored in a given circuit, making insight into device operation essential. This course will cover the minimum necessary for basic analog design. Lecture 2 will focus on MOSFET as a switch, MOSFET structure, and MOSFET symbols. MOSFET as a switch. The symbols of an N-type MOSFET, as depicted in the slide, consist of three terminals: the gate, source, and drain. It is important to note that when operating as a switch, the source and drain terminals are interchangeable due to the symmetric nature of the component. As shown on the upper right of the slide, when the gate voltage, VG, is set to a high value, when the gate voltage, VG, exceeds the threshold voltage, the drain and source terminals of the FET become connected or short-circuited. Conversely, as shown in the lower right side, when the gate voltage, VG, is below the threshold voltage, the drain and source remain disconnected. In this scenario, a high resistance approaching infinity can be modeled between the drain and source terminals. MOSFET structure. The simplified structure of an N-type MOS and MOS device, as depicted in the slide, is fabricated on a P-type substrate, which is colored white. The P-type substrate is also known as the bulk, or body of the device. The device features two heavily doped in regions, colored gray on the slide, that function as either the source or drain. The polysilicon, also known as poly and colored blue on the slide, is a heavily doped conductive piece that functions as the gate in the semiconductor device. Next, the silicon dioxide, also known as SiO2, plays a crucial role in the functionality of the device. Colored orange in the slide, it serves to insulate the gate from the substrate. The key operations of the device take place in the substrate region beneath the gate oxide. It is important to note that the device is symmetric in terms of the source and drain components. Lastly, the vias. This is a metal with high conductivity to provide low resistance connections. Next, we discuss some important dimensions of the device. First is the distance between the two heavily doped N region, the device length L drawn. However, during the device fabrication, the source and drain junction side diffuses, making the device effective length LF a bit smaller. The amount of side diffusion is called LD. Therefore, the effective length is equal to LF equals L drawn minus 2LD. Next is the device width, W, as indicated in the slide. Next is the gate oxide thickness, TOX, together with effective length, LF, plays an important role in MOS performance. For simplicity, we will call LF as just L in this entire lecture. In the early 2000s, typical L is 0.18 micrometer, but as the technology node become more and more advanced, the values of L become smaller, reaching less than 10 nanometers as of this writing. In the reality, MOS is in fact a four-terminal device. We must not forget the substrate in which the device is fabricated. To ensure proper functioning, the source and drain terminals must be reverse biased during operation. This necessitates connecting the substrate to the lowest potential in the circuit. For instance, in a circuit where voltages range from 1.2 volts to 0 volts, the substrate, bulk, or body of the MOS should be connected to 0 volts to maintain proper operation. Now, turning to PMOS, the process involves reversing the doping type. So the doped region now becomes P-doped. Additionally, the substrate is altered to an N-type substrate. In practice, the PMOS device is situated on the local substrate, also referred to as the N-well, which is highlighted in green on the slide. Both NMOS and PMOS devices must be fabricated on the same wafer or substrate, which is why the well configuration is necessary. For PMOS transistors, the N-well is typically connected to the highest potential to ensure that the source and drain regions remain reverse biased. The wafer itself can be either P-type or N-type, simply by reversing the local substrate. However, in practice, the substrate is most commonly N-type. MOS symbols. As mentioned, a MOSFET has 4 terminals: gate, drain, source, and the substrate, or bulk. The substrate is labeled B instead of S, so there's no mix-up with the source terminal. For NMOS devices, the bulk is tied to the lowest potential, while in PMOS, the bulk connects to the highest potential. Sometimes, for simplicity's sake, you'll see the bulk terminal left out entirely. Use the PMOS and NMOS symbols when we omit the bulk for simplicity. In digital IC design, MOS transistors are essentially regarded as switches. The source and drain terminals are considered interchangeable, so the arrow indicators are omitted from the symbols. This results in a simplified representation. End of the lecture.